So last time I was talking about how there are limiting factors within an electrochemical cell. That means that the potential, as we increase the potential, we won't get infinitely great current flowing, just because there are mainly transport effects going on. And I talked about how in about the corrosion of iron with oxygen, and I started describing the anodic current density as a function of electropotential, and that's this reaction here, where you have the dissolution of the iron, and then you have this oxygen going to water, basically. There's 4 electrons there, and it goes to 2 H2O. So now what this looks like as a cathodic current is it goes down like this, as you'd expect, and then what happens is it levels out. Okay, so we expect it to go like this, to continue increasing like that downwards, but instead it is limited. So there's some sort of limiting current, and this is all to do with the transport. And so this is why you're going to go into so much detail about diffusion and convection and electromigration, because it is the main thing that affects the how fast iron will corrode. So if you look at this here, you can see that that it's actually the speed at which oxygen diffuses to the surface of the electrode. That is the thing that will that is the rate limiting step in this chemistry, basically. And so that's basically everything I wanted to explain about that. So we'll go on to diffusion and the limiting currents. So one of the approximations that is used is Fick's law. Okay, so if we're talking about diffusion, you don't go too far before you start talking about Fick's law. And the idea of this is that near to the solid electrode surface, you have a linear change in the concentration of some sort of reaction species. So, out here, what I'm going to plot on the left-hand side here is the concentration, the conc, as a function of distance from this electrode here. And so let's draw it in colour first. So you'd expect lots of species to be formed at the surface, and then as you go further away you have less and less species, until you get to a point where it's not changing. So this is just going to be constant. And then this here is the concentration in the bulk. So this is the bulk concentration, and then this is the this is where it's being generated and diffusing outwards. And so what we can do is we can plot the concentration, and then there's this concentration at the surface, and it comes down, and then we reach the bulk concentration. So this is concentration, this is a higher concentration here, this is the concentration in the bulk. And Fick's law basically says that, well, that's a straight line. So it's a linear decrease in concentration from the surface to the bulk. And in this region here we have convection, so this is kind of turbulence and things are just moving around, and here you have diffusion in this region here. So Fick's law basically allows us to make a description for this limiting current density. So Faraday's law states that the rate of change of molecules at a surface with time is equal to the current and then this factor here, which converts it into converts us from current into molecules. Okay, so this is the thing that converts us into molecules and gets rid of the energy, and so you've got a number of molecules as a function of time. And this is great because we can look at, this is the kinetics, the chemical kinetics, and then on this side we have the electric, current, which we can measure really quite easily. So we link together the electric current and the chemical kinetics, and that's quite a powerful link that you can't get in many other fields of chemistry. So Fick's law is basically that there's some sort of diffusion of, or some rate of change of molecules being produced at the surface, and that the diffusion of those as they go into the solution is linear. And so we have a linear constant, d, and then we have dc dx. Okay, x is the distance, c is the y-axis, and so d is then the slope of this line here, of this line. So we're basically saying that there's some rate of things being formed at the surface, and how that concentration changes as a function of distance is a straight line until you get to the bulk. Okay, and that is we have a look at that when x is equal to 0. So it means we start at this point here, and we say that there's some diffusion into that solution. So now we can relate this here, which is the diffusion, with the electric current by equating these two terms. Okay, and so when we equate those terms and we rearrange for j, we get that j is equal to zfd times the gradient of dc dx, looking at x is equal to 0. Okay, so this is quite cool. So if we have a diffusion constant, there is some maximum current density that we can have if we are considering a system where there is this diffusion constant. And so this is the limited current density for a given diffusion constant. Okay, so in the case of the example I showed you earlier, we can equate this value here, this limited current density, this distance here, with not 0, with a diffusion constant. And that's pretty cool. Very, very helpful. And we can consider, well, what if we can change our diffusion constant? The first thing we need to do is we have to integrate this equation in order that we can kind of consider, well, we actually start at some value at the surface, and then we go to some bulk value, and this only says that, well, it's a constant from the diffusion to that the slope of this is going to be constant. So that's all it says, but it doesn't say, well, where do we start from and where do we end. So we've got to kind of evaluate this equation, and so if we integrate that, we basically end up with the slope evaluated x equals 0 is equal to C0 minus CS divided by D. And D is this distance here. Okay, so it says, well, we're going from C0, which is the bulk, minus this greater value, which is CS up here, and that happens over a certain distance. Okay, so you can think about it like a triangle, and we multiply that by D out the front, and then that gives us the slope of this line. So the concentration is decreasing from some value down to another value, and that's happening over a certain distance. So now, using that, we can define our limited current density as ZFD C0 divided by this small distance. And there's another thing we usually define, which is the mass transfer coefficient, which is helpful when considering things. So Km, which is this constant we made up, and that's the diffusion divided by the diffusion layer distance. Okay, so the diffusion constant, and then this is the distance. Okay, so I mean, if we have a smaller distance and a constant diffusion constant, then we're going to have more mass transfer. Okay, so if we make this distance smaller, we're going to have more mass transfer because it takes less. There's less distance for it to move. There's less distance for it to move from the surface to the bulk. So a smaller distance is good. You get faster mixing. If the diffusion constant goes up, well, of course the mass transfer is going to increase as well because the molecules can move quicker through that solution. And so this is quite a useful constant when we're considering the movement of ions through a some sort of solution. So now we've got J-lim, and we can say that this here is our limiting current for this reaction. So if we're thinking about the breakdown or the corrosion of iron, what we want to do is we want to make this value here as small as possible, right? We want to limit the amount of corrosion that occurs on this electrode surface as much as possible. And so we're going to be considering how we can change the change our mass transfer coefficient, how we can maybe increase our distance, the diffusion layer distance, and that will actually slow down the corrosion. We will consider changing the voltage. So if we change the voltage here, we can reduce the amount of current that's being used we will reduce the current that's associated with this breakdown or this corrosion of the steel. And so that's quite helpful. So that's everything for now.